All right, I'm going to talk about projectiles again. And I want to remind you that when you launch an object from some height horizontally and you look at how long it takes the object to hit the ground, follows a parabolic path, something like this, and you drop an object, that they're going to hit the ground at the same time. That's what that little demonstration I showed you in the previous video shows. All right, so we're going to use that piece of information to calculate how long it takes an object to fall from a given height. And from that, we're going to figure out how long it's going to take to fall or to hit the ground when launched horizontally. So we're going to launch an object from a height of 1.2 meters. By just dropping it. All right, so let's drop an object from a height of 1.2 meters and see what happens. So this is something we did earlier when we did kinematics problems. So you can think about it like this. You can say final equals y initial plus v initial times time minus 1/2 gt squared. We're going to use that equation where y final is the ground, where v initial is 0 because we're just dropping the object, and where of course g, I'm just going to set g to be 10. All right, so let's plug in what we know is 0 first. So we have 0 equals 1.2 meters because we're dropping it from that height. V initial time is 0, so it's minus 1/2 gt squared. And solve for time. And we can say 1/2 gt squared equals 1.2 meters. Therefore, we can say gt squared equals 2.4 meters. T squared equals 2.4 divided by 10 is equal to 0.24. I'm going to repeat this on the next page. So we have t squared equals 0.24. All right, so we need to find the square root of 0.24. Go into my calculator or into Excel if you prefer. Okay, square root of 0.24, I get 0.49 seconds. Great. So that's how long it's going to take for an object that I've just dropped to fall 1.2 meters. So now let's say, instead of just dropping the object, that I'm firing it horizontally. Let's say I fire it horizontally at 2 meters per second. All right, so 1.2 meters, it's going to take 0.49 seconds. But if I fire it horizontally at 2 meters per second, it's still going to take 0.49 seconds to hit the ground. But during that time, it will have moved a certain distance in the x direction. That's what I want to figure out. What distance will it have moved? Well, it's still going to take 0.49 seconds to hit the ground. It's still going to take that long to hit the ground. So if it's moving at 2 meters per second, multiply 2 meters per second times 0.49 seconds, and you get 0.98 meters. It's going to have moved a distance of almost 1 meter. during that time that it falls. All right, so we have a way now of figuring out where an object that's launched horizontally will land, how far it'll land from the starting point. You could do this for any object projected from any height if it's projected horizontally. To be able to demonstrate projectiles, what I'm going to be doing is using this projectile launcher where I can control the angle that the projectile, which is a little ball, will launch from, and the speed. By pushing it to different settings, I can affect how much force the projectile launcher puts on the ball to get it to go up into the air. So then when I release this, the ball will fly up. My goal right now is to determine what is the initial speed of the ball coming out of the projectile launcher. So to do that, I'm going to launch the ball from the ground and see how high it goes, and from that determine the initial velocity using the free fall kinematics equations. So based on how high it goes and the initial height, I can figure out how fast it must have been moving at the start. That'll be the information I need to know about the projectile launcher to be able to do some projectile examples, including launching it horizontally, and that'll be the first demonstration that I do. All right, here's the projectile launcher on my floor. I'm going to prepare the ball to be launched, so I push it in with a pen to get it all the way mounted in there. In a minute, I'm going to pull this trigger, and you're going to see how high it goes, and I have a meter stick here. As you can see, I'm going to move the camera up to here. And I'm going to put another meter stick on top of it here so we can kind of get an idea. This is a little hard to do alone. I'll do the best I can, and we'll see how high it gets. It requires some dexterity here. So here's the launch. And if history has any, I don't know if you could see how high it went. If history has any bearing there, I'll do it one more time with the angle up. It's about 6.04 meter. I'm sorry, 2.04 meters, something like that. In other words, slightly over 2 meters from the launch mouth of the launcher to get to the very top of that trajectory. I'm going to do it one more time. Maybe you can see it at this angle here. There's the top of that meter stick there, the second meter stick. So this is 2 meters high there. That one was a little weaker. Try it one more time. Okay, it's popped all the way down. Consistency is key for this, because I want it to do the same thing when I launch it from other angles. Yeah, just a hair over 2 meters. In reviewing the video that I just took, I disagree with myself. Looks like it was a hair under 2 meters. So I'm going with, it looked like 10 centimeters. I magnified the view when the ball was at the highest point, and looked like it went 1.9 meters above the launch point. So I'm going to use that to calculate what the initial velocity of the ball for the projectile problems is. And I'll do that on paper. All right, I want to do the same thing for a marble. So this is a glass marble. See if it goes to the same height. There's a reason I'm doing this. It's heavier. Looks like it might go a little bit less high on that. I'll take a look at the video to get the measurement. Another one with the glass marble. Meter stick with blue markings. All right, from the video you saw that the yellow ball reached a height of 1.9 meters and the glass marble reached a height of 1.7 meters. The yellow ball went further because it's lighter, so the glass marble was not able to get as high because it had a smaller initial velocity. We'll be calculating the initial velocity of both of these using the approach we learned earlier in the semester for the free fall kinematics problem. So this is the equation that we want to use. We're going to find v initial for both balls, or both objects. The equation we're going to use is this equation from free fall kinematics. V final squared, which is going to be 0 at the highest point. Remember, the ball is going to effectively stop for an instant. It's equal to the initial velocity squared, and that's what we're calculating, minus 2g, and I'll take g to be, I can take it to be 10 meters per second squared for now, and times y final minus y initial, where y final is the 1.9 meters. So if I plug in my zeros and then solve, I get that v initial squared is equal to 2g times y final. So I just plug the zeros in and then rearrange this to solve for v initial. Take the square root of both sides. I get that v initial is the square root of 2 times g times y final. And if I plug in my numbers, I get square root of 2 times 10 times 1.9 meters. And then if I take the square root of that, I get the square root of 38 meters per meter squared per second squared, because g has units of meters per second squared. Probably should have taken g to be 9.8, so I'll make sure I round down. And the yellow ball, therefore, if you take the square root of 38 meters squared per second squared, you'd get 6.16 meters per second. I'll go with 6.1 meters per second. I should have gone with 9.8 right here, but so I'll say 6.1 meters per second as the initial velocity of my yellow ball. As I mentioned in the last video, I found the last segment, 6.1 meters per second squared for the yellow ball. I'm going to do the same thing for the glass marble. I'm going to find its initial velocity. I use the same approach, and I can use the same equation I already derived, which is nice. So I already came up with this equation that the initial velocity is the square root of 2 times g times yf. It's true for both objects. The only difference is that yf is different for the glass marble than it was for the yellow ball. Plug everything in, I get the square root of 2 times 10 times 1.7. Gives me the square root of 34 meters squared per second squared, or about 5.8 meters per second. Just like the other one, I probably should have gone with 9.8 right there. I rounded to 5.8 meters per second.